Welcome, everybody, and thank you for joining us. My name is Maike Prodanovic, and I am Program Director for SIAM Activity Group for Geosciences. It is my great pleasure to introduce Dr. Maike Sonnewald, today. But just before I let her speak, let me just give a couple of slides overview on SIAM Activity Group. So you're always welcome to join us on SIAM Engage. And the link is posted here. And especially, I always like to make sure that students understand that even if your university is not part of the student chapter or a member, there's essentially a way for you to get free student membership. So if you're ever confused how, just please let me know and you can join. And you can join for networking both online and during conferences. Our next conference is in June 2023. So advertising will start full scale pretty soon, but it's a beautiful place to visit in June. So we hope to see you at the University of Bergen. You're always very welcome to find online or contact our officers. So Inga Berg is the chair, Vladimir Drushkin is vice chair. I have introduced myself already, and then Chris Case is secretary. So if you have any suggestions for improvement, please let us know. And now I'd like to introduce our speaker. So Dr. Sonnewald got her PhD in complex systems simulation at the University of Southampton in 2016. And after that, she proceeded to a postdoc at MIT and visiting scientist positions at Harvard, Grenoble, and even UT Austin. Yay! So I was at ISIS, well, about 15 years before you visited. And today she's currently holding a position of the Associate Research Scholar at Princeton, which is in program in atmospheric and oceanic sciences, as well as affiliation with Geophysical Fluid Dynamics Laboratory. And she's also affiliate assistant professor at the University of Washington. So currently she's sampling 2 oceans just outside the United States. So she is a physical oceanographer. She's trying to connect both the actual observations with the most that our computational science has to offer in understanding the ocean's response in a future climate. So without further ado, I will give the floor to Dr. Sonnewald. You can use any way to communicate. This is not a large group, so you can post questions either in Q&A or raise your hand and I will unmute you at the end probably to ask that question. You can use chat to ask questions or say hi or communicate however you'd like. So without further ado, Dr. Sonnewald, I will stop sharing my slides.
Excellent. Yeah, thank you so much for that generous introduction, Maike. Now, I hope you can still see my screen, where the topic that I wanted to talk to you about today was understanding the ocean's response in a future climate, where what my work focuses on and what I think is really important is to be able to provide actionable information for decision makers, where my work looks at things like sea level rise or fisheries catch change. And I know many people here might not be familiar with the important role of the ocean in the global climate system. So I thought I'd just go over this a little bit. And one major thing that the ocean does is it takes up a lot of the anthropogenic heat that we've been introducing. So the oceans have actually taken up over 90%. So understanding the ocean circulation and understanding the ocean's role is very, very important. And for my work, Masa mentioned that I have a background in both physical oceanography and complex system simulation, where computational tools and tools from math are very integral. And I discussed in a recent invited review article how the fields of oceanography and computation, like machine learning, are really moving together in such a way that we can start drawing on these tools from, for example, machine learning, to really accelerate the work that we're able to do. And here I'm showing you just a timeline of oceanography and oceanographic discovery, where the eras of progress are really paced by the tools we have available. And here I'm hoping that with the merger and with an adoption of tools, for example, from machine learning, we can really start accelerating science in a way that's more focused on the data that we increasingly have access to. And we're going to be talking about the ocean, and here's just an example from a high resolution model. This is from the ECHO state estimate at high resolution, and ECHO also has a foothold in at UT Austin, so you might be familiar with it. And what you're seeing here is the surface currents of the global ocean, where the temperature is represented by the colors. So reddish colors are warm and bluish colors are cold. And we can see that there's something, for example, going on in the equatorial region. We can also see that there's something going on here in the North Atlantic. But actually drawing the boundaries here and understanding this in a way that's less overwhelming is really difficult. And this is something that oceanographers have been working on for a very long time, where levels of abstraction are really useful. And this is just an example of how you can represent warm surface currents here and their overall statistically averaged roles, where nominally warm surface currents are brought down to depth by making them very heavy, and then travel along the depth of the sea floor to then be brought up to the surface again in this thing that we can call a conveyor, a global conveyor. So abstractions are really useful. And this is another abstraction. Here we're seeing just a zonal, so a longitudinal longitudinally collapsed version of the ocean, where again this is a cartoon, but overall you can see here in this lower figure that we have these darker blue arrows representing the waters at depth, and here this is the equator, and these are the higher latitudes, so south and north. And overall you can see that you have surface currents that are warm, that are made to sink and travel to then create this overturning circulation. And this is something that we can also represent in terms of how dense or how heavy the waters are, where in these figures to the top here, in the top, the red circulation here constitutes a clockwise movement of water, and the blue ones constitute a counterclockwise movement of water. So here you can see this is represented similarly with a clockwise movement of water and a counterclockwise movement of water. And we can also look at this in depth space. So here's depth on the y-axis rather than density or how heavy the water is on the y-axis. And similarly here we have this clockwise circulation bringing warm waters north, making them dense to sink. And similarly something in the southern hemisphere. So this is a very useful way of looking at the ocean circulation, but of course we're still very muchly so abstracting and making the very complex circulation that's actually there much simpler, for better or worse. And in the rest of this talk I'm going to be using some tools from machine learning, so I thought I'd just very briefly go over what the basic differences between them are, where initially we can think of unsupervised learning as something where the training data we have doesn't have any labels. So here, for example, you could have temperature and salinity, so how salty the water is, that two very important properties for ocean water. And within this two-dimensional space, you could have samples from lots of different latitude and longitudes. And these could be your samples, but you might not be able to know exactly what labels there are. And then with unsupervised learning, what we're trying to do is look for statistically significant lumpings of those data. And here on the here to the right, you can see just an example of this. So for example, the different colors are the different clusters, and the green lines are the decision boundaries that we're drawing between them. And now supervised learning, on the other hand, nominally has labels. So here there are these blue and red dots. And the thing that we want to do here in the supervised sense is draw this decision boundary here to be able to say, okay, some of these are blue, some of these are red. But of course, if we compare this to the unsupervised model, we can see that there is some detail that we're missing here. For example, that there are 3 distinct clusters here. So these 2 different approaches to machine learning are somewhat distinct. But of course, this is, again, a cartoon representation of machine learning. There are a lot of different nuances here. But so just to give an overview of the rest of the talk here, we're going to have 3 different sections. First, we're going to look at the drivers of ocean circulation in climate, and also with a note on weather, identifying what we call dynamical regimes, and look at how we can infer in-depth ocean structures from very sparse data. And secondly, we're going to be actually applying this inference to understand certain components of ocean circulation under climate change, where we're going to be looking at both the North Atlantic and the Southern Ocean. And then finally, what I'm hoping to cover as well is how we can think of this in terms of trustworthy and transparent AI or artificial intelligence, where reflecting on and trying to teach a machine learning method to say, I don't know, or represent its certainty or uncertainty is something that I think is really, really important. And I'm very interested in having a discussion about this later as well, because I think the SIAM community can really contribute there. So jumping into the first topic here, looking at the drivers of ocean circulation in climate and weather, the important thing to realize here is that the ocean really is key for predictability, both of long-range weather, so weather on timescales of weeks to months, and also climate, because it carries a lot of energy. So I mentioned earlier how much heat the ocean has taken up. So of course, the thing that we're really interested in here is why it's taking this up, and also because it can very easily make energy, again, available to the atmosphere. And for the surface here, in terms of measurements, we're very data rich, for example, from satellites. And you can see an example of the currents here again, or the sea surface temperature actually here on the left, where the red colors are warm and the blue colors are cold. And we can see there are patterns here. And the grand challenge here that I see is how we can develop smart ways of monitoring, both for climate and weather applications. So what my work has done here is identify ocean regimes that can act as circulation fingerprints. And these regimes is something that I define as a dominant balance of terms here in the momentum equations, but overall you could think of these as in a much more general sense that I'll get back to shortly, where what my work is doing is using data science or machine learning to determine regimes, where I was able to, in collaboration, determine that there were 6 global ocean dynamical regimes in a full complexity ocean model. And for the concept of dynamical regimes, this is something that you can think of as a parsimonious representation of equation terms. And while this might sound abstract, as scientists, we've been doing this for a really long time. And this effectively is something that you can think of as an allegory to, for example, Prandtl's discovery of the boundary layers solving the hydrodynamic paradox. So being able to find and set up hypotheses of what parts of an equation might be more important in certain areas. And this is something where setting up these hypotheses is something that we can currently now do with machine learning. And this is something that I think is a very exciting topic of research. And for the work that I've done here, what I did was start with the full complexity of an ocean model here, echo 1 degree, And within the full momentum equations, approached naively, these would be intractable. But with my oceanographic background, I was able to take the momentum equation and transform these using oceanographic theory, both enhancing the interpretability because I can now use the theoretical framework that I'm familiar with, and also to reduce the dimensionality. And here you can see this to the left, where the equation that you wind up with only has 5 terms. This is the advective component, so the component to do with being on a spinning sphere, the bottom pressure torque, so the interactions with the sea floor, the wind and bottom stress, the nonlinear torques, and the lateral viscous dissipation. So effectively, for each latitude and longitude, you end up with a 5-dimensional vector. And then within this 5-dimensional vector, you can then ask, okay, are there patterns? Are there these different clusters that I can discover? And for this, I used k-means plus developing a geoscientific model selection criteria. And I mentioned already that, yes, there are 6 of them, and here they are. You can see them on this map to the left. And these colored regions correspond to these regimes. And within these colored regions, we see dominant balances of the different equation terms. So here the equation terms are on the bottom. And we can see that, for example, in the pink region, the wind stress curl, or the component to do with the wind, is really important, and the advective component, so the component to do with being on a spinning sphere, while the other ones aren't really that important. So we can then start to unpick what's actually going on. And for a further description of the different dynamical regimes, please go to the citation at the bottom there. But for now understanding how these regimes are circulation fingerprints, we can just zoom in on the North Atlantic here, where this is now a sketch of the dynamical regimes present, and this was mentioned in the NOAA AI strategy, where we can now understand what these signatures actually mean. And this is what this sketch that I developed together with the very talented Young-Rak Cho shows you. So for example, here on the western side of the basin, we have the stacking of terms or dynamical regimes that signify how the Gulf Stream, this very powerful warm current, lets go of the coast. And this dark blue area shows you how the currents are heading across to the North Atlantic, to the European continent in the transatlantic current or the North Atlantic current. And then these interactions between the light blue and the orange show you where dense waters are being formed. So this way of bringing waters down and creating this clockwise circulation. So in this sense, knowing something about these 2D regimes can tell you something about the 3D ocean features that, for example, are very important for heat transport. So now, knowing about these dynamical regimes, I can go on and do really interesting science with this. And the first thing we did was, together with a collaborator, Redouane Louenzat, was build an inference method to be able to infer these from the surface, or from using only data from the surface. And this is something that we did motivated by the fact that in a lot of situations, we have a lot of data from the surface, but actually knowing something about these 3D circulation structures is very hard for a number of reasons in a number of different settings, including ones that are very important for example, policy decisions. And I'll come back to that a little bit later. But what we did then was very carefully craft a giant labeled data set by using theoretical inference that we were able to glean by having access to the dynamical regimes and knowledge of which terms were important, that we could then use to approximate these terms using data available from the surface. So here the wind stress curl, the depth, and the sea surface height, with which we trained a neural network. And here we use an ensemble multilayer perceptron, where this rooting in theory also helped us guide the architecture that we chose here. And we also very specifically made sure that we had the ability to explain where the skill comes from. So in that sense, the method that we developed, called tracking global heating with ocean regimes, is able to infer the in-depth dynamics using only surface data, And we also very carefully made sure that the deep neural network component avoided a black box component, which is something that I'll get back to towards the later half of my talk. But so just to iterate how this is actually used for a completely unseen model, so a model where you have no knowledge of the 3D fields, what you can do is take this model of interest, extract these surface fields, run this through the ensemble of trained MLPs, and then get your predictions of the different dynamical regimes as a mean of the most probable class. And then with this, we can also come to this explainability aspect of it to understand why these were chosen. So with this, let's jump straight into some of the actual oceanography that we're able to get out of this, looking at ocean circulation under climate change, where one issue here is that with climate model data, a lot of the time we can draw on very interesting intercomparison projects that are a treasure trove of data, but because there's a lot of difficulty in terms of storage and dissemination, a grand challenge here that my work has been targeting is how we can use sparse data to gain full system understanding. And this is, of course, very important because having a better understanding of the system can then help inform policymakers to make decisions that are rooted, for example, in an understanding not only of the mean overall bulk terms, but also, say, things that might influence, for example, sea level on longer timescales. So this data from big intercomparison projects is one like the coupled model intercomparison project, or CMIP. And CMIP is a great tool also because it has contributions from modeling centers from around the world. So these red dots here show you which modeling centers contribute to CMIP. And it's part of an effort from the World Climate Research Program and used as a basis, for example, for the IPCC report, so the Intergovernmental Panel on Climate Change. And it's a standardized experiment framework. So all of these different centers contribute their models that have been run using certain emission scenarios. And this allows a direct comparison of different models. And while this is really a great data set, it also unfortunately leaves a tremendous knowledge gap, because as an oceanographer, for example, I won't be able to analyze this in the way that I might be able to analyze a more local model. And this is because of these large volumes of data where storage and dissemination is a real hurdle. So as an oceanographer, I might be confined to just the surface. And as an example of what this means here, these two figures show you how we can think about and analyze how this overturning circulation has changed in the North Atlantic. So the mean meridional overturning circulation in a historical setting here shows you what the different models might be doing. So these different dots are the different climate models. And if we were to perturb the climate system releasing or abruptly releasing 4 times CO2, this is what would happen. And here we know that something is changing, and we know that overall the overturning circulation would largely weaken, but exactly why and what dynamics are implicated here is very hard to tell from these figures. And just looking at the North Atlantic initially here, this is just to show you how complex the circulation is. So I mentioned that we have the Gulf Stream here. It's a warm current that then heads across the Atlantic, and then it sinks up here in the northern the higher latitudes. And this circulation is incredibly important, for example, for heat transport to Europe, atmospheric patterns, droughts, sea level, hurricanes, what have you. And it's even featured in popular culture here in The Day After Tomorrow. But overall, in a CMIP context, in this climate modeling context, we're often forced to look at this and understand this using only very simple metrics, so bulk metrics, for example, the flow rate at 26 degrees north. And of course, this isn't necessarily sufficient for us to understand these currents in detail. And as an example here, what we can do with THOR, with this method that we've put forward, I was just going to tackle one of the questions that I get a lot as an oceanographer interested in climate, which is, will the Gulf Stream shut down under climate change? And one of the things that, or there are three main things that we can look at in terms of trying to understand this. And here you see a sketch of it. Here's the how the overturning here looks like today with this clockwise circulation that I've mentioned. And here there are three things that we can look for. The warm surface current, this Gulf Stream shifting north, the heat delivery not making it quite as far across the basin, and also that the areas of dense water formation are changing. And with all of these, you would have a weakened AMOC, or a weakened Atlantic meridional overturning circulation that you can see represented in this arrow getting slightly slimmer. So we have some signatures that we know we can look out for. And looking at these now, this is what they would be in a climate model. So here I chose the geophysical fluid dynamics laboratory Earth system model. So that's the lab that I'm affiliated with, where in a historical setting, you can see here that we have this clockwise circulation at the top. The redness here now shows you how intense the circulation is. And then you have the blue circulation here at the bottom as well. And for a historical simulation, we can see that this is quite vigorous. But if we increase the CO2 level in the atmosphere by 1% every year, and now look at the end of the run, so after about 140 years, we can see that the circulation is very much weakened. So there isn't as much of this clockwise circulation. And if we abruptly release or abruptly quadruple the CO2 in the atmosphere, so we have this real delta function, and look at the end of the run again, we can see that this overturning circulation is even weaker. And if we now try to look for these fingerprints, so the Gulf Stream shifting north, the transatlantic current shifting east, and the type and area of deep water formation changing, we can take these surface fields from the GFDL Earth system model and run these through THOR. So run these through this, this machine learning method, and this is what we get. So this is for the historical simulation, this is for the 1% CO2 scenario, and this is for the abrupt 4 times CO2 scenario. And doing this, we can now look at, okay, what components of these dynamical regimes change between the different scenarios. And of course, this is somewhat difficult to just see if one isn't used to staring at these figures, where I've just sort of highlighted the different ones to guide your eyes a little bit. Where now the CO2 forcing is increasing in the X direction, and here we have the historical simulation in the column. To the left, the middle column shows you the 1% CO2 increase, and the one to the right shows you the abrupt quadrupling. And for the Gulf Stream here, this very intense current that brings warm waters up north, we can see that indeed this does shift upwards, so it does shift north. And we can see that this current that brings these waters across the Atlantic and up to the higher latitudes starts off as this trumpet shape here. But as we increase the CO2 perturbation, it becomes increasingly less so, and towards the end, or in the abrupt quadrupling, we really have a very different shape. And we can also see that in the historical area where we have the dense waters normally being formed, in this area, they become very uncertain in the 1% CO2 case, so they're changing around a lot. And in the abrupt quadrupling, we've really changed it quite a bit. So in that sense, we can now say, okay, with this weakening of the overturning, we see these different signals in the overall circulation. And here we only need the surface fields to do this. So in this sense, we can now go on and say, okay, what happens in the other CMIP models? What happens in these other climate model and comparison project contributions? And this is much cheaper to do, and I need access to much less data. And here, just looking at these in 3 different models here now, the CO2 perturbation is increasing, going down, where the CESM model is another American model. And we can see that the changes here include that, for example, the areas of dense water formation here don't really change that much actually between the different models. However, we can see that these, this green area here changes quite a bit, while this, this pink area here doesn't actually change that much. And the UK ESM, or the UK Earth System model, we can see that we start seeing very different patterns in some of the different areas, particularly also in this pink region, where very interestingly also in a French model here, the IPSL model, we can see that we have a very distinct change in how these this blue streak is changing. So this transport across the Atlantic, and also that the areas that we recognize as being associated with the Gulf Stream shift north quite abruptly, which is something that we also see in the UK ESM, for example, but not as much in the CESM model. So in this sense, we can go back to these figures, for example, for the one that I showed initially here, where we only had the different dots to really see what was happening, and unpick more exactly and more mechanistically what's associated with these changes in the overturning. So in this sense, we can compare different models in a much richer way that can also be very, very, very useful for model improvement, because we can more easily look at the different processes that are actually being changed. So with this, I want to jump into another example. Now we're going to move to the entirely different side of the planet. So here we have the Antarctic continent, and the Southern Ocean encircles the Antarctic continent. And there's this current, this incredibly powerful current that encircles the continent more or less. And the Arctic Ocean here, and the North Atlantic, has been projected to be over here, just to show you how central the Southern Ocean is to the overall global circulation. And this is an ocean where warm waters are actually brought up to the surface, so it effectively closes this loop that was started in the North Atlantic. And very importantly here in a climate context, this also means that warm waters are released to the atmosphere, potentially impacting ice. So in this sense, here's a schematic of what happens, in the sense that you have this very strong circumpolar current, the Antarctic circumpolar current, that also interacts with an upwelling of water, so bringing waters up to the surface to release their heat and then become very dense and sink again. And if we now look at this in terms of what happens to the overturning circulation here, we can see that here in density space now, because it's a little bit more intuitive to think of it this way, if we start with the historical simulation, this is somewhat has a blue streak here, so in a counterclockwise circulation, and a clockwise circulation here. That's the part that's bringing warm waters up, and this is increasingly widening as we increase the CO2 perturbation. So in that sense, we know a little bit more about what happens, and now we're going to be trying to assess why that actually happens and where it happens. So now we're looking down in this region in the Southern Ocean, and as a schematic of what these different dynamical regimes here mean, you can see in this this sketch, you have this very strong Antarctic circumpolar current that's coming in. And in the different regions here, we have different things going on. So this gray regime here is a way of looking at how waters are being brought up. So these black arrows here, the colored lines, represent how dense the waters are. And here the lighter blue areas show you where this very strong current is going along, and where there's a lot of nonlinear things happening. While this gray area shows you where this bringing up of waters is happening. And unpicking this again, just to show you the different areas, this is just a zoom in of the Southern Ocean component of this overturning, where we can see that the clockwise component here is largely housed in this Southern Ocean regime, so this gray regime. while the pink regime as well does contribute to this, but slightly less so. And this counterclockwise regime, this counterclockwise circulation, is largely housed in this light blue area. And in terms of understanding the parsimonious representation of equation terms that this actually represents, just a reminder here, we have the pink regime being the wind stress curl and the advective component, while the Southern Ocean component here in gray shows you a very strong balance between the wind stress curl, the advective component, and also the bottom pressure torque, so this interaction with the seafloor. And also, just as a reminder here, in looking at the changes in the ice in the on the Antarctic continent, we know that some areas are much more sensitive than others, and some are really changing quite rapidly. So some areas really have our attention. And in red here, you see areas that are changing quite rapidly. And overall as well, you can see that there's a very big volume change in the ice on the West Antarctic, in the West Antarctic region, while the East Antarctic region is acting somewhat differently. So in that sense, there are some areas that we know might be changing quite a lot, and there's some areas that we think might be responding differently. So if we look at this in a CMIP context, again, we're going to be using the GFDL ESM model and taking these surface fields now from ESM and running them through THOR. This is what we get. So in this sense, we can see certain things that are changing. But again, just to guide your eyes a little bit here and look at this using also different models. What I'm showing here is for the historical sense, the full Southern Ocean regime here, so this gray region where waters are being brought up, and the other two, the 1% CO2 and the 4 times abrupt CO2, show you where the region here, the gray region, has expanded into. So regions where under a climate change scenario, you can expect more of this to happen. And for the IPSL model, the French model, we can see that a lot of the changes are happening in this region. So this is widening quite a bit. While in the CDSM model, we have this happening in the West Antarctic region. So this is this area. This is this area that we were looking at before that was quite red. While in this area, in the UK ESM, we can see that there aren't really as much changes, apart from perhaps in this region. So in this sense, we can use the tracking of this regime to understand a little bit more about what might be happening to, for example, the ice, where we know that this change would significantly impact the carbon cycle, and also, for example, ice melt that would be very important to understand for sea level. So with this, I want to move to the last component of my talk, looking at transparent and trustworthy artificial intelligence, where I mentioned that this was something that we really focused on including in THOR, in this method that I've been presenting, where I think moving to a slightly more general sense here is something that is valuable, because I really think this is a very important topic. And this is because using machine learning as a black box is something that I think is not sufficient for all our scientific purposes, and particularly also not for policy development, for example, so decision-making processes. And the grand challenge that I see here is trying to deliver robust, reliable, and safe tools, whatever your discipline is. And this is something that I discussed in a number of different papers, but a recent perspective in Nature Machine Intelligence goes into this also in a modeling context. And as an example just of what this can look like, on the left here, you see just a representation of the prediction uncertainty in THOR that will also just go into in a little bit more detail. But just to illustrate how prevalent this can be if we move from a traditional framework to a more machine learning based framework, this could mean that even the Weather Service could be racially biased. And as an example of this, here you can see the green regions here are areas where we have excellent radar coverage. And the shaded areas show you here, the gray shaded areas show you the Black population share. And what stands out here is that regions where you have a large Black population share are much less covered by radar. So they don't have excellent radar coverage. And this means that, for example, if you were to train a neural network to do predictions here, you would probably have a skew of good predictions in areas that have a smaller share of Black populations, which, for example, if you're trying to predict hurricanes, would have very real consequences. And similarly as well, there are a lot of examples of how the methods that we've designed have become or can become biased without us realizing and without us intending to do so. And of course, the National Weather Service has no intention of being biased, of course. But here, as a human, we can see that, yes, okay, this is a coarser representation of Barack Obama. But if we run this through a method that's trying to depixelate it, so make it finer resolution, this is an example of what you can get, where, of course, this does not have any similarity to Barack Obama. So in this sense, it's very important to gain an appreciation that even though we don't intend to do this, just by the data we choose to train our models and understand the systems, here for me, that would be the climate system, on the basis of, is something that we really need to consider carefully and double check as much as possible. And here, what the tools that I think are very worth reflecting on for this are both interpretable and explainable, so IAI and XAI. And interpretable AI for me is something that's decomposable, something that we can simulate, and also something that is tractable. And explainable AI is something that happens post hoc, so after the fact, and also gives you local attribution, as well as being able to explain by example. And what do I mean by this? For example, for a neural network, explainability could mean that you train a network and then after the fact, you go through the different layers and understand why those predictions were made. Because in a neural network context, a lot of the time you gain precision by throwing a lot of data at the problem, not necessarily understanding. And of course, in the social sciences, we know that racial profiling can be the result of this, but also within, for example, labeling of hurricanes, a lot of the time this might happen when the people working on this have time to do the labeling, which might accidentally say be on a Thursday. And of course, hurricanes are not more likely to happen on a Thursday, but these biases that are literally just hard-coded into how we do this work is something to be careful of. So in this sense, for the physical sciences, we do have an easier time of this than, for example, for the social sciences, because we can pay with our domain knowledge, with our knowledge of the physical underpinnings of the systems. And this is something that's gaining traction or gaining an appreciation in government as well, where the EU and the US are now calling for more trustworthy applications. And one of the methods here that I mentioned is explainable AI. And one way of thinking about this is in terms of additive feature attribution. So these cover a number of different methods, where the one that I'll be using here or showing here is called layerwise relevance propagation. And this is a way where we can go through a network that we've already trained. So here on the top, you just see an example of a network trained to recognize a cat, where what we do is we set the different weights and biases. And with this, then we can go through, having set these, and understand which components of the system or which areas contributed in the input. So in terms of recognizing this cat, I can see in this heat map that, yes, there are ears here, and we can sort of make out the features of a cat. And for example, that the background here hasn't been picked out. So in that sense, I can proceed with more confidence that, yes, I've actually recognized components of a cat, and perhaps can show the network another picture of a cat that it hasn't seen before, and be more confident that, yes, it can actually pick out features associated with a cat. But of course, we're not interested in cats or dogs, we're interested in dynamics. And here, just as a reminder, we rooted this work in physical understanding. So we took this equation and discovered these parsimonious representations. And now I'm just reminding you of this here, where all the different dynamical regimes really have this meaning encoded into them. And applying layerwise relevance propagation now to the different input features. So here they are on the y-axis, and the different dynamical regimes are here on the top. What I just want to draw your attention to is this Northern Hemisphere Stradrupian regime. This was this pink regime, where what we know from looking at the equation, again here represented on the bottom, is that the advective component, or the component to do with being on a spinning sphere, and the wind stress curl are supposed to be important. And this is indeed something we see here, where I've just drawn out the wind stress curl component and depth here, and the wind stress curl indeed is very important. And we can see that we crossed out this contribution of being contribution of the bathymetry, so the sea floor here H, and indeed we can see that this area here is actively unhelpful. And I know that this is an area where you have the mid-Atlantic ridge, so this undersea mountain chain. So there's a lot of variability in H here. And the fact that this is unhelpful is actually also a great way for me to verify that, yes, the method here has been able to successfully identify physics that I know should be in there. So in this sense, I can proceed with confidence. And another way that I'm moving this work forward is together with a student, Mariana Claire, who's where together we're trying to quantify what trust means within uncertainty estimation within these regimes. And you can see a measure of entropy here on the right, where we're trying to move this into a Bayesian framework. So having distributions rather than a deterministic framework that we were using, although we did have an ensemble approach, but really to try to hard code this Bayesian framework in here and arrive at a meaningful I don't know. If the THOR network sees something in an input that's so far removed from what it was trained on, having it be able to say, I'm not sure what I should classify this as, is something that's incredibly valuable. And we're playing with different additive feature attribution methods here from SHAP and LIAM and also the LRPs, and trying to understand why the regions agree or disagree. We're having this rooting in oceanographic theory is very useful in the sense that we can really try and understand how these methods work and how we can start to improve them, for example. And I also just want to pause for a second before wrapping up in terms of recognizing that or just mentioning that that what we're also trying to do with THOR is to break down some further barriers. So, for example, if you are in a region that might be very severely impacted by climate change, actually studying this in a way that might be most relevant to you can be very difficult, because you don't necessarily have the privileges that you might as a Western scientist. So this is something that I certainly have benefited hugely from, because I've largely had access to computing power, and I also have had access to what we can call data bunkers. So areas where the data has been downloaded and you have access to it, and you have the access to store more data if you need it. But in many countries, this might not be something that they have access to. So for THOR, for the THOR framework, we've tried to combine the access to computing power and the access to data, where the project of another student of mine, Zubair Saibu, who was interested in the El Nino Southern Oscillation phenomenon, was able to work on this using only his laptop and work on 114 gigabytes of data, not having to download anything through this cloud-based framework that we put together. And I also wanted to briefly mention some other work that we're doing in terms of trying to contribute to climate model improvement, where the very talented Aparna Radhakrishnan, who's also been involved in a lot of this work, is trying to potentially run THOR in the model diagnostics task force package from NOAA. And with that, I just want to summarize saying that overall in this presentation, I really tried to highlight a focus on robust and trustworthy method development and method application. And within the three different components here, I think one thing that I want to highlight is that we are at a time where we have access to very large amounts of complex data. And we also have access to tools that we can use to unpick this data and understand this data. And I think we're really at the precipice of a paradigm shift that I've been very proud to contribute to, towards intelligent monitoring and forecasting for climate change mitigation and adaptation. And with that, I just want to acknowledge my collaborators here, and also invite you to go look at the THOR code, go look at the GitHub and the cloud application framework, and also just highlight three different papers here, where the James paper was the THOR paper that I've been talking about, but there's also a review on machine learning applications in oceanography, together with the perspective in nature machine intelligence that I mentioned earlier. And with that, I thank you very much. And I'll stop sharing my screen here.
Thank you very much. This was great. And I would like to, as a start of the discussion, I would like to acknowledge that no equation that involves the curl of the magnetic induction as well as the curl of the wind shear stress should be called primitive equation. You have one slide at the beginning. Primitive equations. I'm like, these are not primitive. Pretty,
that's the name.
These are pretty heavy. So,
but I do agree, primitive might not be the entirely best.
So this is not primitive. This is pretty. All right, we have questions. Yerlan, let me just quickly. I'm going to unmute you so you can ask your questions if you're ready. If not, I will read them out. Here we go.
Thank you very much. I hope you can hear me. So
yes, we can hear you really well.
Okay, great presentation. So first question is just curious about this, the slides where you show that the US and Canada, the seasons and the changes when your CO2 level increases like 1% and 4%, 4 times, I think. Just curious about whether it's winter time or summertime. In the just follow up, is it required to model the wind on the surface over there? Because we talked about the flow, right, ocean, and now we're talking about the surface. That yes, I had kind of confused a little bit, so that part.
Yeah, no, I moved somewhat quickly on a lot of these to try and cover some ground. But what I didn't mention was that we're looking at 20-year mean fields. So in terms of the seasons, this is actually more of an overall understand the new mean state of the climate system. So as we increase the perturbation, a lot of the time the seasonal cycles do potentially change as well, but the overall new mean state that we're arriving at is something that is of great interest. And for the climate models, they include, so they're called Earth system models, which is something that means that they have both an ocean component and an atmosphere component and a land component and the biogeochemical component, and all of these work together. And this is why there's such large amounts of data that disseminating this is difficult. So in that sense, the ocean and the ocean flows are very much so set in motion also by the atmosphere, and the ocean also influences the atmosphere in this very coupled way. So the system is very, very complicated, which is why having this very large model into comparison project is great, but like I mentioned, also a serious hurdle in terms of understanding the details, because storing and disseminating the data is quite difficult. I hope that answered your question.
Mm-hmm. So just and the second question, just follow up. So in flow model, can you comment on the effect of the boundary condition on your 3D numerical like simulations? Because you showed a lot of equations in there.
Could you specify what you mean with boundary conditions?
So we have this advection term and other things like equation.
So this is a fully coupled forwards running model. So what you do is you have the full model and you initiate it somehow. You have an initial conditions, and then it's a free running model. So in that sense, I'm not sure boundary conditions is something that you can that you might have.
Does land pose a boundary in these or not at all?
So you do have continental boundaries, for example, and the configuration of them is of course important. So is that what you mean by boundary conditions?
I thought in that way, but it looks like really complicated model. So it looks like everything's included there, right?
They are
3D. It's in 3-dimensional, I guess.
3-dimensional. There are very many dimensions, and the continents and the interactions with bathymetry are also for the ocean and also for the atmosphere very important components.
So what would be, speaking of boundary conditions, if you don't mind, so what would be, I mean, the land is the wall boundary condition that is not moving, right? So you specify something on that wall, but then there's this coupling of both the ocean and is a wind shear actually a boundary condition, or you're doing both at the same time? Simulation in the atmosphere versus ocean.
Yeah, I mean, these are great questions. It's also, of course, developing these models and refining what we call the parameterizations is a very active field of research that the lab that I'm affiliated with, the GFDL lab, is very actively working on. And the way that these different components work is that they're coupled. And this coupling is something that, for example, happens where you have the wind stress given by the atmosphere, that is, for example, given to the ocean in a certain way, but of course, the ocean also is able to impact the atmosphere. So in that sense, you have a somewhat complex coupling between the two where they talk to each other in a sense. And these actually, this air-sea interaction is something that that I think is very important and that is gaining a lot of attention recently. So this is a great question. So they're to some extent coupled in the sense that you, for example, in a biogeochemical setting, have a model running within the ocean model, for example. But for the ocean and the atmosphere, this is slightly different in the sense that they communicate more regularly,
the interface, which is essentially coupled, both are the boundary for the other.
Yeah. This is why I wasn't
mathematically sure they're boundary condition for that other.
Yeah, I wasn't entirely sure what boundary condition was being referred to here. So thank you for
almost a philosophical discussion. I'm not going to bring it up with my undergrads at all. Anyway, any other questions from the audience? I can just unmute you. Lynn says, oh, Lynn has to go. Thank you, Lynn, for stopping by. She really enjoyed the talk. Did you want to ask a question before you go? No?
Yeah, no, I have to go. I appreciate it though. I've really enjoyed your talk and you've given me a lot to think about.
Thank you. Feel free to contact me also in terms of the THOR methodology or potential input.
Okay, great. I appreciate it. Thank you very much.
Thank you, Lynn. Anybody else has a question? Otherwise, I have one that I'd like to ask. Here we go. Mohammed, I'm going to allow you to talk if you'd like.
Can you hear me?
Yes.
Very nice talk. I kind of heard in the beginning that you were going to use AI to sort of look at surface fields and infer something about the ocean and the deep.
Mm-hmm. And
I kind of missed that in your presentations. Can you go over it again?
Sure. Yeah. The overall premise is that you have these dynamical regimes that are 2D regimes, but the 3D circulation are different components, like the Gulf Stream, for example, is a 3D circulation feature. So it also, when it heads across the Atlantic, is a 3D feature. So it's an undersea current that's very much so impacted by a range of different features that we approximate with these input variables and the deep neural network. So in that sense, all the circulation features that I highlighted are 3D ocean features that you would otherwise not have access to and not know, for example, what this in-depth current that heads across the Atlantic, like why this is moving in this way and that it's there at all. So otherwise you might be looking at just gradients in the salt level, for example, to approximate where the current might be, but there are a lot of other things that can influence this the position of this current. And of course, the areas of dense water formation, this area where dense waters are formed on the surface and brought down to depth, is very much so a three-dimensional feature. So I hope that
all of these features are inferable from the models. I missed how these features are inferred from what we have learned from the AI specifically. So what is AI bringing to the table that I wouldn't learn by running these models?
So the thing that that you're bringing to the table, if I had access to all the data, then you wouldn't need this machine learning method. But unfortunately, for these large climate model intercomparison projects, you do not have access to the data. You're given this wonderful tool, treasure trove of data. But as an oceanographer, I would not have access to, for example, the full current structures or the full temperature fields that I would need to reconstruct these currents. And similarly as well, what I didn't mention was that what I'm currently working on is trying to scale this to higher resolution, where, for example, if you think of the real ocean, to have data from below the surface, we actually need to go there with a ship or a robot. And the ocean is very big and these expeditions are very expensive. So being able to say more and guide this type of exploration using the surface data that we do have access to. So for example, with a satellite, you can say something about the sea surface height and you can say something about the wind stress curl, for example. So in this sense, this inference method and this way of using AI and trustworthy AI, which is something that I really want to emphasize, can be very, very beneficial. I hope that
so if I can summarize, you took surface fields and tried to infer the meridional overturning circulation. Is that?
Not entirely. So this is what we applied it to in this sense because we used a thermohaline setting. But this was something that I also chose to focus on in this presentation. But the circulation features are tied to the overturning circulation and are important fingerprints for the overturning circulation. But in and of itself, we're not saying something about, okay, the overturning circulation decreased by 30% or something. We're saying something about the mechanisms that are associated with these circulation features. So for example, if I were to do this with a satellite field, it would probably look somewhat different. And saying something about the immediate variability of the overturning circulation would be something that would be a lot more complicated because there are a lot more lags involved in the system. So in answer to your question, yes, but it's more complicated.
Okay, fair enough. Thanks.
Thank you for your question.
All right, we're ever so slightly over time. Are you okay with time, Maike? To stay a couple.
Sure, yeah, I'm happy to stick
minutes
around for more questions.
So if you have another question, I can definitely unmute you because we are kind of running a little long. But if there are more questions, we're definitely. My dog has a question. I apologize. I have one more. So in that input layer, what are all of the features that go in the sort of like one of the examples that you're running? What is in the input layer for the neural network?
Sure. Yeah. Also, I also have a dog, and I'm very happy that she hasn't had questions for me or things she wanted to add to the presentation. But so the input layers here are the sea surface height. So how how high up the sea surface is, and longitudinal and latitudinal gradients thereof, the depth, so something that we know, and the latitudinal and longitudinal gradients thereof, and also the wind stress curl. So this is just one field, together with the with what's called the Coriolis term, and this is something that you can calculate on the basis of knowing what latitude you're at. So those are the input fields that we
and
use.
Those are just the vectors, or they're actually structures? Is it spatial structures, spatial data?
Spatial structures. So for the multi-layer perceptron, we do this pixel by pixel effectively, or grid point by grid point. So within each grid point, we take all these input fields, and with the THOR mechanism, so that this neural network, we're then able to say, with probabilistically what dynamical regime would be present here. And in this sense, I also thought it was extraordinary that we had these very coherent patterns that showed up, because really there is no reason for these to be so coherent. They could be pixelated, they could be patchy, they could move around a lot more than they actually do. So in that sense, yes, it's sort of a pixel by pixel, a grid point by grid point process, looking at the correlation features between the different input terms. So within a neural network, this effectively is just a very complex way of looking for these correlation features. So drawing these decision boundaries, like I mentioned in the introduction. And you're muted.
Yeah, sorry. I blame it all, as far as my dog goes, I blame it all on squirrels that are running around. When it comes down to the explainable AI, have you looked into any cases like when, your classification or unsupervised learning really fails miserably as far as a specialist is concerned? So what can you find out if you backtrack that decision, or have you done any work on that?
So sorry, I'll just unpack that.
So when the decision made by the network is bad, have you analyzed those cases to kind of back propagate to the input to see what happened?
Yes. No, this is something that I'm actively working on with Mariana Claire, the student I mentioned, where this is exactly what we're doing. So in this sense, there are some things that are very, very consistently predicted. But with these different additive feature attribution methods, so these XAI methods, for example, LRPs, we can then go back and address exactly what potentially physics were not interpreted correctly, or what the machine learning, the supervised component of the machine learning did that might not be exactly what we intended. But from an unsupervised learning perspective, which is something that I also think is very interesting, nominally my work was purely unsupervised until these XAI methods came to the table, because I really like to be genuinely rooted in physical knowledge, because I think that's where a lot of the interesting science is. Although, of course, the products here are very important for, say, higher level impact from decision making, for example. But there, one of the reasons why I thought this was successful is also because the initial dynamical regime definition, recognition was statistically significant, and I think that the way that you draw these decision boundaries in an unsupervised framework, if the clearer they are and the easier they are to recognize in an unsupervised sense, the more likely you are in a supervised sense to be able to arrive at something that's very certain of what it should be. But again, this is an active area of my research that I think is very, very interesting, because for understanding the source of skill, I think being rooted in physical understanding, which to me means this parsimonious representation of the equations, really gives us a lot of leverage to do this.
All right, thank you. Thank you very much for inspiring talk. You also inspired me to look at my globe from the bottom today, to look at the southern oceans. I don't normally have that perspective.
It's a great ocean. It's very, very interesting physics.
Just overlooked most of the time. Well, thank you once again. And again, this talk will show up on our SIAM YouTube. So if for those who missed the talk, can always go there. Thank you very much.
Thank you so much for the invitation.